Let's take a look at the AVR execution environment before we go further with implementing a bootloader. So the atmega328p chip inside the UNO board has these specs. We have 16 million instructions per second throughput at 16 megahertz, so that's one instruction per clock cycle. And most arithmetic instructions could be executed in one clock cycle. We have 32 8-bit general purpose working registers, which we can use to store data. We can do arithmetic operations on them. We can store or load their values to SRAM. And we have 32 kilobytes of in-system self-programmable flash program memory. This is where we write or read program data, which is very important for a bootloader programmer, right? Because the sole purpose of a bootloader is writing to, in most cases writing to, or in some cases reading from the program memory. So this is very important. This is a very important piece of hardware for us. And we have 2 kilobytes of internal SRAM, which is used for dynamic data stack. It is byte addressable, so you could use it very similarly to the general purpose working registers. The only thing is that you cannot directly address them for an add operation, but you can store and load data from them. So this is the block diagram of the chip. We have the general purpose registers right here. We got the arithmetic logic unit, which takes like 2 operands in any time. We got the data SRAM, which we use to store dynamic data, to store stack information and similar things. It is byte addressable, and we have a 8-bit data bus connecting all of the general purpose registers and SRAM and external I/O modules like SPI, UART, watchdog timer. We even have status and control, like the stack pointer would exist in here, and they are all accessed through the 8-bit bus. Even the program counter could be accessed through the 8-bit bus, even if it's not 8-bit, even if it's 16-bit. Okay, so let's take a look at the general purpose registers. We have 32 of them. They're all 8-bit wide. The only thing to note here is that the last 6 ones are grouped in 2 to form pointers. So these pointers could be pointers to data SRAM or the data memory, or they could point to program memory in some cases. In AVR architecture, all addresses and consequently all pointers are 2 bytes, which is called a word. So the pointer size is 2 bytes. And this is why these X pointer, Y pointer, and Z pointers are 2 bytes wide. So on the right, we have some basic arithmetic operations like add with carry, subtract, or subtract with carry, or multiply. In all of these instructions, the left operand is the destination operand, and both of them are the source operands. So they are going to go through the ALU, and the results will be written back to the general purpose register. We also have data transfer instructions like move, which moves some data in R0 to R1. Move could only be executed among registers. You cannot move from a data location to a register. The move word instruction would move the contents of R2 and R3 to R0 and R1. So let's take a look at the next type of data transfer instruction, which is a load. So this loads directly from data memory, loads directly from a data memory location. In this case, the data memory location is 200 hex. And 200 hex corresponds to an SRAM location in our case. So this is taken from the datasheet too. The data memory map is like this. The 32 registers are mapped with these values, and the 64 I/O registers, which may include the status and control, the SPI unit, the interrupt unit, the watchdog timer, or analog comparator, or EEPROM registers, or even the program counter, are going to be in the 64 I/O registers. And maybe the UARTs, like maybe the extra ones, like UART, SPI, or other stuff, are going to be in the 160 external I/O registers. They're going to be in these addresses. After these addresses, the internal SRAM addresses will start. So this is like 2 kilobytes of SRAM. There's a little typo here. This should be 2048. So a load instruction would load the value inside this address to the general purpose register R0. So the data is going to flow like this. In contrast, a store operation would store the value inside a general purpose register to a data memory address. In this case, this data memory address points to SRAM, so the data flow would be like this. Let's take a look at another store operation. In this case, this 4E address does not point to the internal SRAM. It points to an I/O register. In this case, it points to the SPI data register. So the data flow would look like this. Then we have program flow type of instructions. They're going to manipulate the program counter basically. So jump 100 would write 100 to the program counter. So in most of these cases here, we are using the 8-bit data bus for our operations. Most of the normal instructions do that. And let's take a look at how consequent instructions will get executed in this architecture. So we have program addresses here and instructions on the right side. We are going to load two values from data SRAM to general purpose working registers. So at the start of these instructions, the program counter will be loaded with the address of the first instruction. And then the instruction itself will be fetched from program memory. And then it's going to be executed. But while the first instruction is being executed, the instruction fetching resources are free. So while the first instruction is being executed, we can fetch the next instruction simultaneously, which is depicted here. So while the first instruction gets executed, is fetched, nothing is done in addition. But when the first instruction is executed, simultaneously we can fetch the next instruction. This is possible because the fetching of the next instruction does not use the data bus, it uses the program memory bus. So this is a reason why the data memory bus and the program memory bus are separated in the AVR architecture. So we can do a simple pipeline of execute and fetch in the AVR architecture. And this is how it can provide a 16 million instructions per second per 16 megahertz clock cycles. This is how it can provide that throughput. So after that, it's going to fetch the next instruction while it is executing the second instruction. So the concept of data memory and program memory being separate and their buses being separate is called Harvard architecture. This is in contrast to von Neumann architecture, where there's single memory, it's used for instructions and data, and there's a single bus. So now let's go back and think about what we are doing. We're writing a bootloader, we're implementing a bootloader. What a bootloader does primarily is manipulate the flash program memory. So it needs to write a new program to be executed. But in our case, it's going to take the data from a UART module to the general purpose working registers, and somehow it's going to call some instructions in a predefined manner to program the flash memory. And these instructions are called store program memory and load program memory. Note that the operands of these instructions are not specified here. This is because programming flash memory cannot be done in bytes. Flash memories usually have a page size. So you take a block of a page. In our case, it is 128 bytes. So you take a block of a page, you write your data to a page, then you're going to call store program memory to store the contents of that page to the flash memory. Most of the time, this is how we're going to use store program memory instruction. And load program memory works similarly. So one thing to note is, like, why are these separate instructions from load and store instructions? Like a load instruction, a normal load instruction would, let's look at the data memory map. So a normal store instruction would load from either a register, an IO register, or the internal SRAM. So it cannot load from a flash program memory, as it is not byte, I don't want to say addressable, but it's not byte programmable or byte readable. If you're going to read from it, you're going to read a whole page, or if you're going to write to it, you're going to write a whole page. If you're going to erase some memory, you're going to erase the whole page. So we got SPM and LPM, and we're going to use them a lot. And these instructions are somewhat overloaded. We are going to use SPM in a lot of ways. So there is a site or like hidden memory page somewhere here, which is 128 bytes wide, and we're going to write data to it through the store program memory instruction. And again, using the store program memory instruction, we're going to store the contents of that hidden memory inside the permanent flash program memory. And when load program memory executes, we're going to load some value from that hidden page of flash program memory. So I think that's enough for now. I think this video provided some background for the AVR architecture to be able to implement a bootloader or understand the implementation of a bootloader. So thank you for watching, and see you in the next video.